So 20 years ago, I was doing physics, and then, like most of my colleagues, I ended up in finance. And about 11 years ago, I moved to California to do what nowadays is called data science, basically using R, machine learning, database, this kind of things. And I'm also teaching at 2 universities machine learning lately. And since I'm living in the US, I have to put this disclaimer, so my employer has nothing to do with this work. And this talk will be about machine learning with R. And of course, we hear all these people who never used R telling us that R is slow and really unfit for machine learning. So we'll see how this goes. So, and one of the reasons why people are telling us is because everyone thinks nowadays that they have big data, and obviously you cannot do big data with R, but actually my view is quite different. So my view is that most people don't really have big data, so you are actually better off in using like a single server with a lot of RAM, just fit all your data into RAM and do analytics in R or Python or any of the single server packages. So how much memory can we get? Nowadays it's very easy to get like 100 gigs of RAM for under $1,000, or you can get a terabyte of RAM in your server, or you can, with a few clicks, go to the cloud. This instance with 250 gigs of RAM has been available for at least 3 years, and now there is an instance on Amazon that has 2 terabytes of RAM. You can go to the other cloud providers and get similar amounts of RAM. And then how big are the data sets that people are working, especially in machine learning? So what matters is not really the raw data, but more like once you did the feature engineering and you do the machine learning on the data metrics, how big is that? So there are various surveys on how big are these data sets that people are working. Here is one, and basically it seems like most people are working with a few gigabytes of data and a few million records at most. So if you don't have big data, then don't be ashamed. You are not the only one. So I started with this premise that someone has a few gigabytes of data, a few million records, and I wanted to see which tools you can use to use binary classification. So binary classification is probably one of the most widely encountered use cases in machine learning. So I looked at various open source tools and tried to do binary classification up to 10 million records. So I picked the data sets. I picked a data set. We'll talk about that a bit later. And the question is what algorithms and what implementations to look. So there are these 2 papers from 2006 that are still very relevant, I think. They have taken like more than a dozen data sets, a dozen algorithms, they implemented them, and a couple of performance measures. And the ones that are the top in accuracy are random forest. There will be a lot of random forest in this track. Neural networks, now deep learning is a big buzz. And also boosting, they're pretty accurate. I didn't want to deal with support vector machines because they don't scale linearly with dataset size. So you cannot really do support vector machines nonlinear on more than a few 100,000 or a million records. And then I want to look at logistic regression. Is a simple model, but it's a good baseline. So I will be dealing with that. And what tools I looked at? So I talked to my friends, I looked up Kaggle forums, and I kind of figured out that the things that open source tools that people are using mostly are R packages, Python scikit-learn, VoPowerBit for linear, H2O, XGBoost, Spark, MLlib, and there are a few others. And I did a short survey at a machine learning meetup in Los Angeles, and this was the percentage of people using those tools. So it's kind of, it validates that thing. And all these tools, they make a lot of promises, like they are all fast and distributing and scalable and optimized and parallelized. So I was wondering how much of that is true. So I took a data set, the well-known airline data set, and I did some experiments on EC2 so that you can reproduce yourself. I looked at scalability, so I increased the data set size on a logarithmic scale up to 10 million records, and I looked at training time, RAM usage, and AUC. So since this data set is a few gigabytes of data, the 10 million records, I think, is like 2 gigabytes. You don't really need distributed computing, so single server and tools that work on that are fine. And I looked at a few distributed tools, but they also work on a single server. So this is not Kaggle, so when I looked at accuracy, I don't necessarily want the best accuracy, but I want something pretty close to best. Also, the training time, I want something that finishes, doesn't run forever, and RAM usage, I want it to fit in this big memory instances on the cloud. So all the code is on GitHub, and I tried to get as much results with as little work as possible. So I really don't think this is like a comprehensive benchmark. It's pretty simple, limited, and incomplete. So if you want to complain about it, then you are welcome to submit a pull request. And of course, benchmarking is hard. So whatever I do, it will be wrong anyway, but maybe it will be useful for some people. So the first thing I looked at linear models just as a short baseline. And on these sizes, like 10 million records and under, you can do logistic regression. For example, with any of the tools, it's very easy. It trains in a minute or two. It doesn't use more than a few gigabytes of memory. So it's really trivial to do logistic regression in any of those tools on the sizes. So random forests. Here there is some kind of surprise. So you would think that everyone implements the same textbook algorithm, but there are so huge differences in training time or even memory usage. So there is like 10x, even 100x difference in training time between different tools. And we'll see later this is related to various low-level optimizations that people are doing to make things faster and better. So unfortunately here, the random forest, the R random forest package originally by Leo Breiman is pretty slow. So I've been using that for many, many years, but on like small data sets, a few 10,000 records, but you cannot really use it in any same way over a few 100,000 records. But that's obviously not the fault of R. It's like an old package written in Fortran and not maintained, and there have been many new tricks since then. So the best two that are like the fastest are XGBoost and H2O, and we'll see later that both have packages in R. So as R users, we can just use them. And Spark is a big hype with all this big data thing, and it's kind of slow in also using a lot of more memory than the other options. So the best ones are the ones that have been written by people who know about high-performance computing and how to do various hardware low-level optimizations. For example, how you fetch the data in the algorithm so that you keep as much the data in L2 CPU cache as possible. You can get 10x speed up. You can see this paper about XGBoost, for example. And we are lucky as our users, so both XGBoost and H2O, they have packages from R. With Spark, they had also some kind of accuracy problem, which I pointed out to the Databricks guys. So they gave me something that they thought it's fixed, but it's still not. And then they promised also to make it faster and use less memory. So Spark 2.0 came out almost a year ago. So they have a nice data frame API. Basically, they invented the data frame. And I was expecting that they fixed these things, but no, actually, it's even slower now. And it's still broken in accuracy. So ironically, on bigger data, it doesn't work. So at this point, I kind of gave up on Spark. So if you play with the parameters, this is H2O, you can get accuracy of 80% with random forest. So the best linear was about 71%. So you see a complex model can capture better the structure in this data set. Next, I will talk a little bit about boosting. So it's a bit more complicated. You need a little bit more work. You can also overfit, so you need to do something called early stopping. And the scalability is very similar. So the best tools, XGBoost, H2O, and you can get, with a lot more work of tuning, you can get up to 81% AUC. So there is a new package, open source by Microsoft, LightGBM, and there is also like an R package for that. So everything is written in like C++ or C or Java, and then there are these wrappers in R or Python. And now lately, LightGBM is actually the fastest, so it's faster than XGBoost or H2O, but you still might want to use XGBoost or H2O for other kind of features. There are also people trying to implement this on GPUs with some kind of encouraging results. So this is another repo I have, and things change fast here. So keep in mind, people are looking to do this on GPUs. And why? Because deep learning is a huge hype. So this is Andrew Yang telling everyone that you shouldn't use only deep learning because it's beating all the other algorithms. And of course, he's a great guy. He's been a founder of Coursera. He had a great machine learning course at Stanford and then on Coursera. So deep learning doesn't work really that well on all kind of data sets. So for instance, on airline data set, which is very similar to things that people have in businesses, like if you do fraud detection or churn or this kind of problems, then boosting is usually better than deep learning. So my view on this thing is summarized in this suite. So for most of my problems at work, like GBM is beating actually deep learning. But as our users, we are lucky again. So we have various options to do deep learning. Now the latest is our Keras package, just published by RStudio maybe a few weeks ago. And it's using the TensorFlow backend, and it's as good as the Python ones. So I think R is really a great tool to do machine learning. So we have all this high performance, random forest, GBM, deep learning, whatever you want, packages available from R. They have really nice interfaces. We have all these other packages to do statistical modeling that's kind of unparalleled in any other environment. On the other hand, the big data distributed computing is really hard, so those things are still have less features, they are slow and kind of buggy, so you kind of have to decide where you want to spend your time. Do you want to spend time fighting the tools, or you want to do some real data analysis? So I think for a data scientist, our job is to get out some value or insight from data. So I would recommend using the best tool for the job. So be productive and use the tools that work the best. So thank you so much. We are ready for questions, or contact me on any of these channels, or talk to me after the talk. Thank you.
Thank you very much, Tyler.